this lecture we are going to solve some problems involving momentum of particles and momentum of a stream of particles. So, first problem that we solve is a gun fixed on a trolley where mass of unloaded gun plus trolley is m0 is free to move on a frictionless track. So, let us make this. Here is the trolley and here is the gun loaded on this, a gun put on this, and this total mass without any bullets in the gun is m0. It is now loaded with n bullets of mass small m each. So, now we put n bullets in this and each one has mass m. The bullets are fired one by one. Find the final speed of the gun plus trolley after all the bullets have been fired. So, now notice that this is a problem of conservation of momentum. So, what is happening? Just like if you have a single gun and you fire a bullet, the gun recoils. Exactly the same thing is happening here. Oh, I forgot to write something. The relative speed or velocity of the bullet with respect to the gun is u. Now, what happens in the single case? Suppose the mass is m0 and there was one bullet inside m. As the bullet comes out, it goes out with the speed u with respect to the gun. So, if the gun is recoiling with speed v towards the left, then you have speed of bullet with respect to ground is going to be u minus v. Then only with respect to the gun, the speed of the bullet would be u. So, what we have then in the single gun case, initial momentum of the system is 0 and final momentum is going to be minus m v if the gun has, or let me call this m0, gun has recoiled with speed v towards the left, plus m u minus v is equal to 0, which gives me v equals m u over m plus m. Notice that v is coming out to be positive because minus v is actually the speed of or velocity of the gun. If you took v to be positive, then what will happen is that you will get m0 v plus m. If v is positive, that means the gun is going this way and the bullet is going this way with speed u with respect to the gun, then the speed of the bullet with respect to the ground would be u plus v will come out to be 0, and then you get v equals minus mu over m plus m, and this minus sign tells you that gun is actually going to the other direction. Now what is happening in this problem, that after the first bullet is fired, the second bullet comes in, then the third bullet comes in, and so on. So initial mass in the present problem of gun plus trolley plus bullets is equal to m0 plus n m. After the first bullet is fired, the mass is going to be m plus n minus 1 m, and its velocity is v1 plus m u plus v1 is going to be equal to 0 by momentum conservation. This is equivalent to this equation here, and this immediately gives me v1 is equal to minus mu over m 0 plus n m. So after the first bullet is fired, the gun is moving with this speed v1. What about the second time? Now you see, when this is happening, so after the first bullet has been fired, v1 is equal to minus mu over m plus n m, and momentum of gun plus trolley plus n minus 1 bullets is equal to minus mu over m plus nm times whatever mass is left, and that is m0 plus n minus 1 m. And after the second bullet is fired, this momentum is conserved. So I am going to have whatever the leftover mass is, m0 plus n minus 2 m, and suppose the velocity becomes v2 plus m. The speed with respect to the ground is going to be v plus u plus v2. This is going to be equal to minus mu over m0. So this is m0 plus nm in the brackets m0 plus n minus 1 m, and this gives me m0 plus n minus 1 m v2 is equal to minus mu minus mu over m0 plus nm m0 plus n minus 1 m, and therefore v2 is equal to minus mu over m0 plus n minus 1 m minus mu over m0 plus n m, and so on. Now you can calculate the third one and fourth one, and I can actually look at the pattern and see that my answer after n bullets have been fired is going to be v2 is equal to minus mu over m0 plus n minus 1 m minus mu over m0 plus n m. You do the next step just like we did for v2, you will find that v3 will come out to be minus mu over m0 plus n minus 2 m minus mu over m0 plus n minus 1 m minus mu over m0 plus n minus 0 m, which is same as minus mu over m0 plus nm. And seeing this pattern, you can immediately write that Vn after n bullets have been fired is going to be minus mu summation k equals 0 to n minus 1 over m0 plus n minus k m, and that is your answer. If you do not like this finding a pattern, let me do it in a different way. And what I am going to assume is that the speed, or to be more precise velocity, because I am also worrying about the direction positive or negative, is Vk after k bullets have been fired. So, after k bullets have been fired, the mass of gun plus trolley plus n minus k bullets is m0 plus n minus k m, and therefore, the momentum of this system is going to be m0 plus n minus k m times Vk. And now we fire k plus 1th bullet with relative velocity u with respect to the gun, and the speed of m0 plus n minus k plus 1 m, this many bullets, is v k plus 1. Then by momentum conservation, we are going to have m0 plus n minus k plus 1 m v k plus 1 plus m u plus v k plus 1, that is going to be the momentum of the bullet plus the leftover bullet and trolley and gun, and this should be equal to the initial momentum, which was nothing but m0 plus n minus k m times Vk. This immediately gives me m0 plus n minus k m v k plus 1 plus mu is equal to m0 plus n minus k m Vk, or Vk plus 1 is equal to minus mu over m0 plus n minus k m plus Vk. That is my governing equation. Now, I can do step by step. When k equals 0, that means no bullet has been fired, V0 is 0, and therefore, V1 is going to be equal to minus mu over m0 plus nm, that is my V1. When k equals 1, I know V1, so I want to find V2 from this. V2 is going to be minus mu over m0 plus n minus 1 m, because k is 1, minus I put V1 mu over m0 plus n m, and so on. So, you can build up the speeds one by one and get the same final answer. The next problem that I do is on momentum of two particles and their center of mass. A particle of mass 0.1 kg is moving with a speed of 2 meters per second along the x-axis. Another particle of mass 0.2 kg is moving along the y-axis with the same speed. So, what you are given is I have x and y axis, x, y, I have one particle of mass 0.1 kg moving this way with 2 meters per second, and another particle of mass 0.2 kg moving this way with same speed 2 meters per second. And what we want to find is 1, find the net momentum of the particles, and 2, the velocity of their center of mass. So, solution: the net momentum is going to be P equals P of particle 1, let me call this particle 1, let me call the one moving along the y axis particle 2, plus P 2. So, I can write this as 0.1 times 2 moving along I plus 0.2 times 2 moving along j. So, net momentum is going to be 0.2 I plus 0.4 j kg meters per second. That is solution number 1. For 2, velocity of center of mass is nothing but net P divided by the net mass. So, this is going to be 0.2 I plus 0.4 j divided by 0.3, which is 2/3 I plus 4/3 j meters second inverse. So, the wave center of mass and the momentum are in the direction of this, where a slope is exactly 2. So, the slope phi is such that tan phi is equal to 2. Question number 3. This is again on the center of mass, and this is a small block of mass m, like a point particle, it is very small, is on one side of a half cylindrical cavity made in another large block of mass m. So, what is shown is, here is this large block of mass m, here is the cylindrical cavity, and there is a small block sitting here. Let me show this in a different color. A small block of mass m sitting here. The mass of the large block is m. The radius of the cavity, is r. So, this is the radius of the cavity. The small block slides along the cylindrical surface. How much would the large block have moved by the time reaches the other side. That means what we are asking is that this small block, once it reaches this side, how much would the large block have moved? Further information is the center of mass of the large block is right in its middle, and there is no friction. So, center of mass of the large block is right along this line, somewhere here. So, let us see what is happening. To solve this problem, let us see what is the situation in the beginning. In the beginning, the large block is like this, and its center of mass is in the middle, right here, and the small block is sitting here. After the small block has moved, the large block has also moved with respect to its initial position. I am making it slightly larger, and this was its initial position. I will take the coordinate system such that x axis is this way and y axis is going up. So, this is the y axis here, this is the x axis, and it has moved. The large block I will take as if it has moved by a distance x0. You may wonder why I am taking x0 to be positive. It does not matter, because in the end, if x0 or the bigger block moves to the left, it will come out to be negative. So, since there are no external forces, the CM should not move. So, what I will do is I will calculate the CM position in the first case, this case. I will calculate the CM position in the second case after the block has moved to the right side and equate the two. So, let us see, xCM in this case is mass times x position of the large block, which is 0, plus m, the small block, and its position, which is minus r, divided by m plus m. And the position of the CM in the second case is going to be m times x0 plus the distance from x equal to 0 of the small mass is now r plus x0. So, this is going to be m times r plus x0 divided by m plus m, and these two should be equal. If I do that, I find that minus mr is equal to mx0 plus mr plus mx0, or x0 comes out to be minus 2 mr divided by m plus m, and that is how much the block would have shifted, and this minus sign tells you that actually the block shifts to the left. So, final position, if I were to make it, is going to be something like this, with the red block being here and it being shifted, the middle being shifted by this much distance, which is magnitude is 2 mr over m plus m. The next problem that we consider is when a stream of particles or a stream itself, continuous stream, hits a surface and transfers momentum to apply a force. So, this problem is, assume that water stream coming out of a water tap is flowing vertically down and has a constant diameter d. It strikes a surface which is at 45 degrees from the horizontal, and the water flows along the surface after striking it. If the speed of water before hitting the surface is V, find the force and pressure on the surface. So, the problem we are solving is, here is a water stream coming down and striking a surface which is at 45 degrees from the horizontal, and after striking the water starts flowing like this. This diameter is d here and velocity of hitting is v. We want to find the force that is applied on this surface here and also the pressure at this point. Now, if I make the picture again, if I look at this surface, water comes in, it brings in momentum P per unit time, and then it starts flowing along the surface. So, what is happening? There is a change in the momentum, and this change causes the force to be applied on the surface. Now, momentum coming in per unit time is going to be equal to mass per unit time times the velocity. Velocity is given to be v, and mass per unit time is going to be the area times rho v. Area is pi d square by 4 times rho v, and therefore, momentum per unit time that is coming in is equal to pi d square by 4 rho v square. Out of this momentum, this component which is perpendicular to the surface, this momentum is transferred to the surface, and the momentum which is parallel to the surface keeps going that way. So, when water hits here, there is a force that is applied by the surface on the water to stop it from moving perpendicular to the surface, and this force by action reaction, in turn the water applies the same force on the surface. So, the force is equal to momentum transfer per unit time to the surface, or more specifically, momentum transfer per unit time normal to the surface. So, let us find this component normal to the surface. This is 45 degrees. So, P cosine of 45 degrees is equal to pi d square over 4 rho v square cosine of 45 degrees, which is equal to pi d square rho v square by 4 root 2. That is the momentum that is being transferred per unit time to the surface, and therefore, let me make this picture again. When water comes here and starts flowing like this component of momentum perpendicular to the surface becomes 0. So, momentum transfer P per unit time normal to the surface we have just calculated is nothing but pi d square by 4 rho v square, and that is the force divided by root 2, and that is the force that water applies on the surface. What about the pressure? Pressure is going to be equal to force per unit area. Now, when water strikes the surface, which is at 45 degrees, notice that this side is slightly elongated. So, the area is not pi d square by 4, but slightly larger. And how much larger is it going to be? This is going to look like an ellipse with this distance being d and this being larger by a factor of root 2, because this horizontal distance is d, this is hypotenuse, this is going to be d root 2, because this angle out here is 45 degrees. Therefore, the area is going to be larger by root 2. So, area of ellipse is going to be pi d by 2 times d by 2 root 2. This is pi a b, which is pi d square by 4 root 2, and therefore, pressure, let me write a different color, pressure where the water strikes the surface is going to be force divided by the area, which is going to be equal to pi d square rho v square by 4 root 2 times pi d square by 4 root 2, which is half rho v square, and that is your answer. The next two problems are going to be dealing with variable mass. So, the first problem I am going to do is, suppose there is a table and on the ground there is this chain which is being pulled. Let this height be h. So, let me state the problem now. A coiled chain of mass lambda per unit length is on the floor with its upper end being held at the edge of a table of height h. 1. Find the force needed to hold the chain. 2. If the chain is being pulled by a constant speed v, find the force required to do so. And 3, if instead of being pulled by constant speed, the chain is pulled by a constant force F, then find the rate length per unit time at which it uncoils. Ignore friction and any horizontal movement on the floor. So, let us see. Here is the table, and if I am holding the chain at this point applying a force F, then first part, all I am doing is that I am balancing this portion of the chain, which I will show by red here. So, its weight is lambda times h and the weight is times g. So, the force required to hold it there is lambda h g. In part 2, when I am pulling it with constant speed v, then in addition to this lambda h g, which is required to hold it there to balance this portion shown by these curly brackets, I am also changing the momentum of the chain. Although it is moving at a constant speed, the mass keeps on changing, the mass that is moving, that keeps on changing. So, the force required is going to be lambda h g plus dm by dt, that is the change in the mass, times v. And what is dm by dt? Dm by dt is a speed v times lambda. So, F therefore becomes lambda h g plus lambda v square, and that is your answer. We can check dimensionally that this is the correct answer, because lambda h g does have units of weight and lambda v square is mass per unit length times L square t raised to minus 2, which is also has the same dimensions as the force. Third part is interesting. In this part, instead of pulling it with a constant force, we are pulling a constant velocity, we are pulling it with a constant force. Again, the same equation works, that the force is going to be equal to lambda h g plus d by dt of m v. But notice this time, because the force is constant, as the mass keeps on increasing, mass which is being pulled is increasing, the speed is going to change, and therefore, I am going to have lambda h g plus dm by dt v plus m dv by dt. Let me work this equation out at an instant when x length is on the table and this height here is h. Therefore, the total mass of the chain is going to be h plus x times lambda, and dm by dt is nothing but dx by dt times lambda, which is lambda v. And therefore, the equation that I get is going to be F equals lambda h g plus lambda v square plus h plus x dv by dt. What I am interested in is finally finding out dx dt equals v, which is the rate at which the chain is being pulled. Notice here that I have the variable x out here, which is changing with time, but t out here. Therefore, it will be nice if I could change this variable t to x, and that is what I am going to do next. So, I am going to write dv by dt is equal to dv by dx times dx by dt, applying the chain rule for differentiation, which comes out to be v dv by dx, which becomes 1/2 d by dx of v square. And therefore, this equation out here becomes F equals lambda h g plus lambda v square plus, there is a lambda I am missing here, lambda h plus x 1 half d by dx of v square. This is the equation that I should be solving. So, what is the equation that I am solving? F equals lambda h g plus lambda v square plus 1 half lambda d v square over dx, and there is something at the top also, there is h plus x here. That is the equation that I am solving. Let me write in this in the standard form. I will write this as 1 half lambda dv square over dx h plus x plus lambda v square equals f minus lambda h g. Notice that the right hand side is a constant, and this equation is a differential equation for v square. There are standard ways of solving it. So, first let me write v square, therefore is going to be v square homogeneous plus v square particular, where v square homogeneous is the solution of the equation 1 half lambda dv square homogeneous dx h plus x plus v square equals 0, v square h. This is a very standard equation and I can solve it very easily, and that gives me v square equals some constant, let me write this homogeneous, over h plus x square. That is v homogeneous, v square homogeneous. What about v square particular? I will take this to be a constant equal to f minus lambda h g over lambda, and you can see directly that when I differentiate this, this gives me 0. So, this satisfies the equation. So, therefore, my solution for v square is nothing but c over h plus x square plus f minus lambda h g over lambda, where c is a constant to be determined by initial conditions. What are my initial conditions? We have got v square equals c over h plus x square plus f minus lambda h g over lambda. My initial condition is that v square is equal to 0 when x is equal to 0. That means when I just started pulling the chain from here, when x was 0, v was 0, and that gives me 0 equals c over h square plus f minus lambda h g over lambda, or c equals minus f minus lambda h g over lambda times h square, and therefore v square can be written as f minus lambda h g over lambda minus f minus lambda h g over lambda h plus x square times h square, which is equal to f minus lambda h g over lambda 1 minus h square over h plus x square, which is f minus lambda h g over lambda x square plus 2 h x divided by h plus x whole square. That is my v square, and therefore, the speed v is going to be 1 over h plus x square root of f minus lambda h g over lambda x square plus 2 x h, and this is dx dt. This is the rate at which the chain is being pulled if I apply a constant force F. Next problem is a rocket problem and very standard problem, which is, this is problem number 6. A payload of 1000 kilograms is to be accelerated in free space, that means no gravitation, to speed of 6 kilometers per second. The fuel from the rocket is ejected at 5 kilometers per second with respect to the rocket. Neglecting the mass of empty rocket, find the amount of fuel needed to do so. So, this is a standard application of rocket equation which says that the final velocity is equal to u, which is the relative velocity between the gases being ejected, log of m initial divided by m final. We are given that we want to attain a speed of 6 kilometers per second with u being 5 kilometers per second. Notice I have not bothered to change kilometers per second because the units are going to cancel, times log of m initial by m final, and this immediately gives me that m initial by m final is equal to e raised to 6 by 5. Now, m initial is going to be 1000 plus mass of the fuel, and m final is the payload mass 1000, and therefore, I have 1000 plus mass of the fuel is equal to 1000 times e raised to 6 by 5. So, m fuel is going to be 1000 e raised to 6 by 5 minus 1, which comes out to be roughly equal to 2320 kgs. So, that is the amount of fuel that you need in this rocket to accelerate this payload of 1000 kilograms to 6 kilometers per second if the relative speed between the rocket gases coming out and the rocket is 5 kilometers per second.